This one is sample 14.813. This one asks for the max and minimum values of the function f subject to this constraint. And so, once again, we're going to use Lagrange multipliers to set up this equation. We'll take the gradient of f and set that equal to lambda, the Lagrange multiplier, times the gradient of our constraint function. So let's take those two gradients. So first the gradient of f, and that's pretty easy. It's going to be 6, 3, 2. And then we need the gradient of g, our constraint, and this one's more complex, but not too bad. There's no cross terms, so this is 8x and 4y and 2z. Okay, so now we can set up the beginning of our system of equations. Remember, we're going to get 4 equations with 4 unknowns. The constraint is 1 equation, and then the other 3 are going to come from the gradient equation. Okay, here they are. So 6 is equal to 8x lambda. Our second equation is 3 is equal to 4y lambda, and our final one is 2 is equal to 2z lambda. Well, each one of these has no cross terms in it. They're all independently defined in terms of lambda. So the best way to find lambda is to actually solve all these for lambda and then plug it back into the constraint equation, and I can use that to solve for lambda, and then I can come back here to solve for each one. So let's solve each variable in turn for x, y, and z. So x in the first one is going to be equal to 3 over 4 lambda. That's the same for y, is equal to 3 over 4 lambda. And then finally z, because the 2's cancel, is equal to 1 over lambda. And now I'm going to rewrite our constraint equation in terms of lambda. So it will be, instead of 4x squared, it's going to be 4 times 3 over 4 lambda quantity squared plus 2, and instead of y squared, it's 3 over 4 lambda quantity squared, and plus z squared, which is 1 over lambda squared, and all that will equal 70. Okay, so working this out, this is going to be 9 over 16. Now it's just 9 over 4, so it's 9 over 4 lambda squared plus, this one's again going to be 9 over 16. Now it's going to be 9 over 8. 9 over 8 lambda squared, and then plus just 1 over lambda squared equals 70. So moving some things around, 70 lambda squared will equal, these three fractions are 9/4, 9/8, and 1, so I'm going to make it 18/8, 9/8, and 8/8. So it'll be 18/8, 9/8, and 8/8. So summed up, those will produce 35/8. The 35 and 70 cancel and just give me 2, which I can divide by. So this will be equal to 1/16 is lambda squared. So if lambda squared is 1/16, then lambda is plus or minus 1/4. Now I'll have to take both possibilities into account, so let's go back here and see what we get for the possible x, y, and z values of these critical points, points that could be maxes or mins. So for x, it's equal to 3 over 4 lambda, and lambda is plus or minus 1/4, so it just makes plus or minus 3. Y is equal to 3 over 4 lambda, so it's also plus or minus 3. And then finally, z is just 1 over lambda, so that's plus or minus 4. So this creates a real problem in that x could be either plus or minus 3, so could y, and so could z. So it ends up giving me 8 potential sets of points from 3, 3, 4, all the way through -3, -3, -4. Now, these are the only 2 that I've actually retained. All the rest of them are irrelevant because I'm looking for the max or min. And of course, we look at the original function. It's just x plus y plus z. So the minimum value will come when x, y, and z are as small as possible, and the max will come when x, y, and z are as large as possible. So if I replace any of these internal terms with negatives, it will be smaller than the max, but larger than the min. And so I don't have to test all of them. I can kind of use common sense and say, this is going to produce the max, and this is going to produce the min. So let's go ahead and do the substituting. This is going to be f equals 6 times 3 plus 3 times 3 plus 2 times 4, and that's equal to 18, and 9 is 27, and 8 more is 35. And of course, the other f is going to be -35. And there they are. That's the max, and that's the min. And if the function weren't so easy, I might have had to test more of these, but this one was pretty easy by inspection.